We are at Sunset Beach and they're digging clams by hand, and it requires only labor input. The total number of clams obtained per hour is given by Q is equal to 100 times the square root of L, where L is the labor input per hour. Part A says, graph the relationship between Q and L. Now, anytime a question asks you to graph the relationship between Q and L, or between any two values, all you need to do is find some values for any of the two variables and you calculate for the other one. You can just find values for L, just think of any random values for L, and you calculate the corresponding value for Q. So let's try that. So for L, let's take values 0, 25, 50, 75, 100, and if we were to calculate the values for the corresponding values for Q given these values of L, so you just substitute these values into this equation here, then you would get 0, 500, 707, 866, and 1000. And that you could use these two set of points and plot your graph for part A, and the graph should look like this. Right? Now part B says, what is the average productivity of labor output per unit of labor input in Sunset Bay? Graph this relationship and show that output per unit of labor input diminishes for increases in labor input. And we'll do part C one time. Part C says the marginal productivity of labor in Sunset Bay is given by MPL is equal to 50 divided by the square root of L. Now you can calculate the MPL simply by taking the derivative of the original equation. So if you take the derivative of this with respect to L, you would get the MPL. It says that graph this relationship and show that labor's marginal productivity is less than average productivity for all values of L. Explain why this is so. To get the average productivity of labor, it is equal to Q divided by L, which is equal to 100 times the square root of L divided by L, and this is equal to 100 divided by the square root of L. So you find some values for the average productivity of labor and some values for L. You'll use the same values from before, 0, 25, 50, 75, 100, and you substitute these values of L into this equation now. So this equation is the equation for the APL. Then you would get 0, 20, 14.1, 11.5, and 10. Right? But that's the APL. Now let's consider part C, which talked about the MPL. So the MPL, and they calculated first, this set is equal to 50 divided by the square root of L. All you need to do, again, is the same thing. MPL and L, you just think of some values for L, so we'll use the same values. And you calculate it, you substitute these values into this equation here, and you calculate the corresponding values for the MPL. And you should get 0, 10, 7, 5.8, and 5. So now that you have these set of values, you can use this to plot your two graphs. So these values would be used to plot your MPL, and these values would be used to plot your APL. And the graph should look like this. And as you can see from the APL, so in part B of the question, it says, graph this relationship and show that output per unit of labor input diminishes for increases in labor input. So as you can see, as labor input increases, the output per unit of labor diminishes. And it's the same thing for the marginal productivity of labor as well. Part C of the question says, to show that labor's marginal productivity is less than the average productivity for all values of L. And this is the answer for that. Since the APL is everywhere decreasing, then each additional worker must contribute less than the average of the existing workers, bringing the average down. Therefore, the marginal productivity of labor must be lower than the average productivity of labor. And it's given by this equation here, where the MPL is actually equal to the APL over 2. And you can see that from these two equations. The APL is 100 divided by the square root of L, whereas the MPL is 50 divided by the square root of L. So the MPL is actually half of the APL. Right? And I hope that answers this question. Thank you for watching, and I'll see you in the next one. Goodbye.